Hello, hello, hello. Hello, 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 check, hello, 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 hello. आवाज आ रहा है?
Hello, 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 hello.
Hello. Good afternoon, everyone. A very warm welcome to all the dignitaries, respected faculty members, our distinguished speakers, and dear students. We are truly honored to have you all here for today's special session. This event holds great significance as it gives us the opportunity to learn from esteemed experts in the fields of nuclear energy and automation. We would like to take this moment to express our sincere gratitude to INAE for conducting and supporting this enlightening session. Let us now extend a warm and traditional welcome to our distinguished guests. I would like to call upon our dear Principal Ma'am to present them with the bouquets. It is my honor to introduce our first speaker. Shri A.K. Balasubramanian is a mechanical engineering graduate from Regional Engineering College, now NIT Calicut. He completed 1-year orientation course in nuclear science and engineering from BARC. He was Director, Nuclear Power Corporation of India Limited and was a distinguished scientist of the Department of Atomic Energy prior to retirement. He is a Fellow of Indian National Academy of Engineering. He has a vast experience and expertise in design, engineering, safety analysis, technology development, procurement, construction, commissioning, aging management of nuclear power plants, and project management. He is well versed with regulatory processes and licensing of nuclear power plants. He has participated in many international conferences and discussions on nuclear reactor technology. During his illustrious career of about 37 years, he contributed immensely towards indigenization of pressurized heavy water reactor and its further development. This technology in India has grown to a state of maturity over the years with an excellent record of safety and availability. He was a member of NPCL Board of Directors. He was also a member of Board of Nuclear Fuel Complex and Heavy Water Board. He is a recipient of Distinguished Alumnus Award from NIT Calicut. Currently, he is busy teaching nuclear engineering and nuclear reactor project management, besides being a member of Regulatory Review Committee of Atomic Engineering Regulatory Board. He is the co-chair of INAE Mumbai chapter. I would like to call upon Sir to introduce us to INAE and its activities and deliver his lecture.
Honorable Principal Dr. Jayalakshmi, Dr. Sangeeta, other faculty members, my dear students, ladies and gentlemen. Good afternoon to all of you. Good afternoon. At the outset, let me thank the management of VSIT for giving us an opportunity to conduct one of the initiatives of INAE Mumbai chapter, that is Student Outreach Program. I would like to put on record our sincere thanks to all of you. Thank you. INAE, that is Indian National Academy of Engineering, is a premier autonomous body working on supporting engineering and technology in the country. So I will take a few minutes to show a few slides on INE to make it a little more clearer. As you can see, it's an autonomous professional body. It comprises of India's most distinguished engineers, engineer scientists, and technologists from all the engineering disciplines. So essentially, it's an engineering professional body. It promotes practice of engineering and technology and related subjects of its application, giving a support to the national program related to engineering. Okay. Now, so you can see here the individual points here. It promotes and advances the best practices of engineering and technology. It has instituted what is known as professorships, fellowships, studentships, scholarships, and so on. So maybe some of you can also interact with INE as students. And a whole lot of activities are promoted and conducted by INE, the headquarter being Delhi. We have local chapters, and INE Mumbai chapter is the agency which is conducting this program, and so on behalf of the INE Mumbai chapter, I once again express thanks to all of you. So here we can see presidents, past presidents and the current president of INE. You can see Dr. APJ Abdul Kalam, Dr. Chidambaram, Dr. Anil Kakodkar, Dr. Kasturi Rangan, and so on. All very famous personalities have been, and the current president is Mr. J.D. Patil from L&T, Larsen & Toubro. So it has got a mix of academic engineers, R&D professionals, as well as industry engineers. So that mix makes it very important. Well, today, yeah, thank you. This is the introduction about INE. Today, in fact, we have a speaker, Dr. Padmanabhan, who will speak to you about the topics suggested. Before that, I would like to take a few minutes from you. You know, if you look at the dream of today, the 1.4 billion population India, what is the dream? The dream is to make the country a developed nation, a developed country by 2047. That's the dream that we are having today, and how this will be achieved. As you all know, a developed nation means a high level of economic capability or high level of prosperity economically, advanced industrial infrastructure, advanced technological infrastructure, and a good standard of living. These are the three basic parameters which will kind of delineate the developed nations from developing or underdeveloped nations. So India is a developing nation, and we are moving towards the status of a developed nation. That's where the role of engineering and technology is very vital. So what do engineers do? Engineers design, engineers build, engineers maintain structures, equipment, systems, processes, and so on. They innovate, they drive change. So The dream towards developed nation will be essentially fulfilled by the engineers of today and tomorrow. So therefore, the future uh, by 2047, you are going to be in the nearly around 40 years age, and you will be the actual leaders who would do this. So our hopes and expectations are on you. Therefore, we selected a topic apt for this occasion, that is evolution of engineering as a backbone to the modern society. The topic will be delivered by a very eminent engineer, Dr. Padmanabhan. So I will not come between you and the topic. I am not planning to talk about atomic energy today. So thank you very much, and may you all achieve your dreams. May you all contribute towards the overall shared dream of reaching a developed status for India, maybe by middle of this century. Thank you very much. Thank you.
Thank you very much, sir, for giving us a brief introduction about INA and its activities. I now take great pride in introducing our second speaker, Dr. Padmanabhan Mahadevan. Dr. Mahadevan graduated in Electronics and Communication Engineering from Mahatma Gandhi University, Kerala, and joined the 36th batch of the BARC Training School. Currently, he heads the Machine Intelligence and Automation section and the SEM Development section in the Security, Electronics and Cyber Technology division of BARC. His work spans remote inspection tools, analytical instrumentation, and cyber physical systems. May I now request Dr. Padmanabhan to address the audience.
Thank you very much. So let me also start with putting on record my appreciation and gratitude for this opportunity. I thank both VSIT as well as INAE for providing me an opportunity to interact with budding engineers, students who are going to be shouldering the responsibility of nation building. So we are all engineers over here. When we look at engineering, we look at it as a profession. But if you look deeper, engineering has been something more than a profession. It has been a way of life. Development of technology and development of engineering has always played a pivotal role in shaping the way society evolves. Right from the beginning, if you see that the way society has changed has always been anchored on some technological advancement or others. So today, rather than going for a particular topic, what we thought, we will talk to you about how engineering, how technology and science has evolved over the period of time and how it has influenced the change of society. Also, whenever we engineers meet, we always have a feeling that, okay, I am a civil engineer or a mechanical engineer or electronics or an IT person or a computer science person. And today it is this era or that era and so and so. But if you look at it, all the part of the engineering plays a pivotal role in developing the technology. We cannot achieve any technological advancement based only on one branch of science. We are all together, and together we are here to go to make our country a developed nation. So let us have a look at how So let us just have a look at how technology changed and how human evolution happened. See, if you look at the history of human civilization, Homo sapiens, as we call, we go millions of years. We have a history of millions of years. What was the first thing that actually propelled a change in human civilization? It was the discovery of technology or discovery of technique to control fire. Fire was there in nature, and we were always afraid of fire till we learnt how to control it. So, learning methods of creating fire and controlling was one of the pivotal changes which brought the human beings in control. This happened millions of years ago. We actually don't know what was the date, but it was millions of years ago. The next thing was development of stone tools. So this we attribute to the Paleolithic age, approximately 2 to 3 million years ago. So with the development of stone tools and with our knowledge of controlling fire, we became what we known as a society of hunter-gatherers. And we existed as society of hunter-gatherers for next few million years. After that, we learned how to domesticate animals. We learned how to use the stone tools. We settled down and started agriculture. So we became an agrarian society. And along with that came the next big important discovery or invention, that was the invention of wheel. What you see over there is the oldest record or oldest remain of wheel found in Slovenia. This is about 3500 BCE old. So it's a wooden wheel and a wooden axle, possibly a part of a potter's wheel. So the history documents that the invention of wheel could have been much even older than that. That propelled society further. Then from the Bronze Age, let us jump few thousand years, couple of thousand years ahead. The next thing which revolutionized human society is what is seen in the screen. It is the invention of steam engine. Steam engine, who invented steam engine? Pardon? Okay. So some people say Stephenson, some people say James Watt. But the invention of steam engine did not come in one shot. Okay, it started somewhere in 1678. There was Thomas Savery. He came up with an idea that if you have a chamber, you introduce steam into the chamber, allow the steam to condense, then it creates low pressure. That low pressure can be used to lift water. So he came up with an idea of making a pump using steam. That was the first known record of steam engine. From there, it evolved. It came to another engineer or another technologist, Thomas Newcomb, who introduced the concept of piston and cylinder. Again, it was a low pressure steam engine. Then slowly it came to James Watt. The contribution of James Watt was he introduced a separate condensation chamber, and he also introduced a method for converting this reciprocating motion into rotary motion. And that is what led to the Industrial Revolution. But even James Watt's engine remained a low pressure engine till 1800. That is because he held a patent on this, and nobody was willing to work on something which was already patented. When the patent expired in 1800, then other people stepped in and they were able to develop what we know as steam engine, that is the high pressure steam engine. After that, the next revolutionary invention was the way to generate electricity. Electricity was also known in nature. The first sources of electricity were chemical. But chemical sources, that is using cells, cannot be used for mass consumption. Generation of electricity through electromechanical means is based on Faraday's law of electromagnetic induction. So what you see on the screen is a model of Faraday's device which was used to generate electric power. We'll come to this later. Then after that, the next revolution came was the birth of electronics. But what I have shown over here are not semiconductor devices. They are vacuum tubes, because electronics started with vacuum tubes. After electronics, Then the next revolution that came about, next revolution once we had electronics, the next revolution that actually changed the world was computers. Next. What you see here was the first digital computer. We will again come to this. Then after computing, with these inventions, our society shifted from an agrarian society to an industrial society. The next technological change came was telecommunication. The launch of satellites, and this happened somewhere in 1950s, and after that what you see is the invention of chips, electronic chips or microprocessors. What you are seeing over here was the first microprocessor made by Intel. It is Intel 4004. It used to operate at a clock speed of, can you take a guess what would have been the clock speed of this microprocessor? It was hardly 700 kilohertz. Today we are talking of gigahertz. This was just 700 kilohertz. It was a 4-bit processor. Today's processors are all 64-bit processors. We are talking of 64-bit platform operating systems. So this was a 4-bit processor. So this is how the computing started. And then came the internet. So with this, our society shifted to what is known as a knowledge-based society. Now let us go through how these inventions happened. We will not go to the stone tools and steam engine. We will start from electricity. So the first source of electricity which was used was chemical source. It happened in 1800. This is attributed to Volta. What you see is a Volta cell which are having electrodes dipped inside an electrolyte, and this voltaic cell was able to generate electricity. And once we had electric current, a lot of studies happened. People started studying effects of electric current. They were trying to see what all things happens. Oersted found out that electric current leads to magnetic field. So the moment we came to know that electric current can produce magnetic field, the immediate question was, is the other way around possible? Can magnetic field generate electric current? So a lot of experimentation happened, a lot of people tried, but nothing worked till the next person came into picture. That is Michael Faraday. So with Michael Faraday coming into picture, he found out a way how magnetic field can create electric current. Next. So what you see over here is the famous experiment demonstrated by Michael Faraday to Royal Society. So you see there is a ring or a circular core and with two windings on it. One winding is connected to a galvanometer, the other winding is connected to a battery. In this configuration, there is no response from the galvanometer. The moment you break the circuit, that is when you connect the battery or you take it away, the galvanometer starts ticking. So this led to the postulation or led to the theory that the change in magnetic field is what is responsible for generating electric current. It is not the magnetic field, but the rate at which it changes. And this helped Michael Faraday to build this device. You see, this device is a simple generator. There is a horseshoe magnet, you can see in the orange color. This is actually a model kept in Tokyo Museum. And then there is a copper disc. And there are two electrodes connected to the copper disc, one from the center, one from the periphery. If you rotate the disc, then the disc spins at a speed and the linear velocity at the center as well as at the periphery is different, leading to two different flux linkages, and it generates a EMF difference, and then there is a current. So this is what Michael Faraday found out, and immediately after this dynamos and motors followed and the revolution took place. Electrical engineering was born. But let me tell you, Michael Faraday was the person who found electromagnetic induction. But the numerical treatment to electromagnetic induction, finding out how exactly things work, had to wait for the next scientist, that is Maxwell. All the people, all of us know these famous Maxwell's equation. See, the first two equations, we know it is the Gauss law. The one in the center is the Faraday's law, which actually links the change in magnetic field with EMF. So it took Michael Faraday to put all these things. This is actually the backbone of electrical engineering or for all electrical sciences today. These 5 equations, they drive electromagnetics, electrical engineering, optics, anything to do with electromagnetic waves stem from this. Now let us come to birth of electronics. Okay. Let me ask you a question. Who do you think should be credited with the discovery of something that led to electronics? Okay, I will show the picture. Can you recognize this gentleman? This is Thomas Edison. But we don't remember Thomas Edison for electronics, do we? We remember him for something else. We remember him for lamp, electric light. Thomas Edison is considered to be the most practical scientist in our history. He never worked in theory. Whatever he did had a practical purpose. When he was trying to perfect the electric lamp, he tried a particular configuration. In this configuration, you see there is a loop. That loop is the filament. And inside, he inserted another electrode. And both these, that electrode and the loop, they were connected to external circuits outside. What he found was, there was a current flow happening between the electrode and the loop, even though they were separated by vacuum. Nobody knew why this happened. This happened because of thermionic emission. But at that point of time, electrons weren't discovered. Nobody knew they were fundamental particles called electron. So this effect is known as Edison effect. Edison noted this effect as a very interesting phenomena, but of little practical consequence. But it is this discovery of Edison that revolutionized the world in a way nobody could have imagined at that point of time. Edison also noted that if you connect a potential in a particular manner, the current flows. If you connect it in the other way, the current does not flow. But since electrons were not discovered, he could not find out how it happened. So the discovery of electronics had to wait till 1906 or 1904 for this gentleman, John Ambrose Fleming. It was Fleming who is credited with the invention of the first electronic device, that is the diode valve. Diode valve immediately found applications in radio. Then people started tinkering around with this. They introduced a third electrode, called it triode, then came tetrode, pentode, and afterwards came semiconductors, and the whole electronics started. So once semiconductors came, the world got filled with semiconductors, discrete components, integrated circuits, VLSI devices, and we forgot vacuum tubes. So now let me ask you a question. Do we use vacuum tubes today? How many of you have seen vacuum tube, a vacuum device? Now, do we use vacuum tubes today? We may feel that no, we don't. Let us have a look. I am sharing this graph I have borrowed from CERN Accelerator School. We all know what is CERN. It is the European Nuclear Research Center, the place where Large Hadron Collider was made. So CERN Accelerator, this slide is taken from a course from CERN Accelerator School. X-axis shows power in kilowatt. Y-axis shows frequency. So when you are close to the origin, low power, low frequency. That is power in the order of 10 kilowatt or lower. Frequency is up to couple of megahertz or maybe even touching gigahertz. You have all semiconductor devices, transistors, MOSFETs, FETs, tunnel diodes and all those things. But the moment you go above, going to hundreds of kilowatts or go to the other side, going towards gigahertz or the combination of both, we are going to gigahertz with higher power, then semiconductors are not available today that can do the job. That is where you have vacuum tubes like klystrons, traveling wave tubes, etc. So even today, when we want high power radio frequency, we have to rely on klystrons or traveling wave tubes. Defense applications, high power radars, high power RF for accelerators, even in your microwave oven which you are using at home. What is the source of microwave? It's a magnetron. Magnetron is a vacuum device. So even today, vacuum devices do exist. And we are having in our Department of Atomic Energy, we are having a big accelerator program. And for the accelerator program, we need high power RF amplifiers. So where do we go? We are trying to develop them. So what you see next is a high power RF amplifier. This device is 1 meter long. It is a S-band klystron. Okay, it's a RF amplifier. Now, when I say that I have to design a RF amplifier, which branch of engineering comes into your mind? Who is going to do the major design of this? Of course, we'll all say electronics, right? Most of the design is electromagnetic. So you need electrical engineers as well as electronics engineers to do the electromagnetic design. But the entire structure is actually a mechanical structure. You need mechanical engineers to design it. Electronics engineers cannot do that. We can only give electromagnetic design of the klystron. But the actual klystron has to be designed by a mechanical engineer. You see the schematic of klystron. There is an electron gun. Then there is a RF section consisting of resonant cavities. Then there is a collector. This klystron that we are trying to build is a S-band klystron. S-band means 2 gigahertz to 4 gigahertz frequency. It is going to operate at 130 kilovolt. The beam current will be 90 amperes. The peak output power that is going to come out of this amplifier is 6 megawatt. Now somebody will ask, if I have to deliver 6 megawatt, how much power will this device draw? What is the efficiency? The efficiency is only 45%. So I will have to pump in 13 megawatt of power to get 6 megawatt. So where does the remaining power go? Any idea? It goes as heat. So thermal design of this device is the most critical part. So the topmost part, the collector, is where the heat dissipation happens. We have to cool it with water. We need water lines to cool it. So the whole device is designed with the inputs from mechanical engineers, electromagnetics and electronic engineers together. So all of us together only can build this. So this is one of the critical devices for many applications including defense. Okay, now let us come to the next point, that is the evolution of telecommunication. How did telecommunication start? How did people communicate in olden days? So olden days, what we had something known as visual telegraph. You have heard of semaphores. What are semaphores? Semaphores are basically symbols. So if you see there is a tower, this was designed by a French entrepreneur, and or you can even call him an engineer, Claude Chappé. This happened in 1792 at that time. Before that, people used smoke. So here on the tower, you see there is a device which can be raised up and lower down to create different symbols. These symbols are called semaphores. From the line of sight, somebody will be sitting and watching and noting it down. That is how telecommunication started. It went like this till electric current came into picture. People understood how to use electricity to send signals. That invention is credited to the next gentleman, Samuel Morse. We have all heard about Morse code. Morse code is what made telegraph possible. So he found out that by making and breaking an electric current, we can send signals as dots and dashes, and he generated a code through which we can send telegraphic messages. So this is the basic telegraph instrument which was devised by Morse. This happened in 1830. Now the moment he was able to do this, the whole world started scrambling to use it. Now how do we use it? For using that, we need to run wire from one end to another. Then started a hurry to lay down cables. People started laying cables between cities. Then they thought, why not connect America and Europe? So this is a painting which depicts what happened in 1854. They tried to lay a transatlantic cable. The cable was laid from Ireland to Canada. If you look at the map, Ireland and Canada are the closest distance across the Atlantic. So from 1854 to 1858, it took 4 years to lay this submarine cable. And after that, in 1858 August, the first signal was sent, and it was successful. It was so successful that people immediately jumped and they started using it. And you know the result? The cable failed in 3 weeks. 4 years of effort went down the drain in just 3 weeks. In 3 weeks, the cable failed because nobody knew what a submarine cable should be. What will happen if you put a cable under the sea? What all things we have to do? Today we know. Today's submarine cable looks something like this. See the outer sheath. You are having a polyester outer sheath, a polymer outer sheath. Then you have mylar tape. After that comes the armor, steel braided armor. After that you have a water barrier made out of aluminum or some other material. Then you have polycarbonate, another water barrier of copper or aluminum. Then after that you have petroleum jelly to seal it from water, and in the end you have the optical fibers. So this is the construction, a typical construction of an undersea submarine cable that we use today. So the telecommunication revolution also led to the cable industry. We had different type of cables coming in, cables that can withstand harsh temperatures, cable that can withstand fire, cable that can withstand saline atmosphere, cables that can withstand submersible conditions. So this evolved in another direction. So when this was happening on the ground, so next slide. Next. When this was happening on the ground, something started happening in the sky. This was 1951. Russians took the lead. They launched Sputnik. Sputnik was the first communication satellite. It carried radio transponders. It carried radio receivers and transmitter. And they were able to communicate to different parts using this. And the moment Russians took the lead, Americans followed. Then started the space race. Next. America came with its Telstar series of satellites, communication satellites, in 1960s, and afterwards we also joined. We started with the Rohini series of satellites. They were not actually communication satellites, but then slowly we came to Aryabhatta, Bhaskara, and then we launched our INSAT series. INSAT series were the communication satellites, and today the latest satellite that ISRO has put is GSAT-24, which has 20 channels of KU band. You know, KU band is 14 to 20 gigahertz. This is used for DTH services. So this whole thing has been already, actually the satellite was launched for a private company, so which can provide DTH services. Now when we talk of satellites, till now we were talking about communication satellites. What is special about communication satellites? Communication satellites target a particular area of the globe. So in order to stay there, they have to be put in geosynchronous orbit. Geosynchronous orbit is how far away from Earth? 36,000 kilometers away. So if you put it at 36,000 kilometers, they will be orbiting with a 24-hour period and they will be staying put on a particular place. So that is the communication satellites. But today, apart from communication satellites, we are having so many low Earth orbit satellites also. They are used for remote sensing. And one of the most important series of satellites that come under the slightly lower orbit is the GPS satellites. And then another series of satellites have come up. I want you to guess what this picture shows. This has been in news recently. It is Starlink. Now what is Starlink? Starlink is a constellation. Back. Starlink is an idea of SpaceX. The idea is to use a constellation of satellites to cover the entire Earth. Their plan is to put something like 12,000 small satellites, cover the entire Earth, so that even in the middle of a jungle, we will be able to get broadband connectivity. They are targeting 100 to 150 megabits per second. Now, this endeavor has led to certain technological advancements. The first is, how do you build 12,000 satellites unless you go for mass manufacturing? Till today, satellites were tailor-made. They were made by specialists, scientists with special hands. As long as we keep doing it in a special way, we don't really call it engineering. The engineering comes when you can document everything, put it on drawing and hand over to anybody and that person is able to duplicate. SpaceX has started mass manufacturing satellites. The second innovation is Starlink satellites are at an orbit of 500 kilometers above Earth. So they are not geosynchronous. Starlink satellites move with a velocity of 27,000 kilometers per hour. So if I put an antenna down and if my antenna can see 100 degrees, the satellite will zip across that 100 degrees in just 4 minutes. So what happens after that? That is why you need a constellation. The next satellite comes into picture. So you start communicating with the next satellite. Okay. But have you ever seen a satellite dish? Satellite dishes are directional antennas. They have to look at the satellite. Now what happens if the satellite is zipping across at 27,000 kilometers per hour? My antenna will also have to move back and forth. So every 4 minutes I have to rock the antenna, which is not possible. So that is why they came up with another technology that is called phased array. Electronics people will be able to understand what is phased array. Phased array is actually, instead of having a single antenna, you have an array of antenna. And then you excite this antenna in such a way that the resulting beam goes in different directions. So what you see is a dish of the Starlink dishy. They call it Starlink dishy. The Starlink dishy has got more than 1,000 antenna points. And all these antenna points, the software inside that takes the GPS coordinates of the station and it knows which satellite is coming up. And accordingly, it modifies the beam. Now that is, every orbit has got an orbital velocity. In order to balance the gravity, the centrifugal force depends on that. So at 500 kilometers, the orbital velocity is 27,000 kilometers per hour. So this is another technological advancement that SpaceX and Starlink has brought in. So today, what is going to happen? After SpaceX, some other agency will also start. And very soon, you will find our sky filled with satellites. We will not be able to even have a clear view of the sky. Astronomers have already started raising this concern because ground-based astronomy is at risk. You try to focus on some faint star, but you will find satellites zipping through your view. Next. So this is how the orbit is looking like. You see there is a GPS satellites. Above that you have a, geostationary orbit. Below you have iridium satellites, that is the sat phones. Then you have our 500 kilometer Starlink. You have remote sensing satellite, International Space Station. Almost all the orbits are filled. and the topmost orbit is called as the graveyard orbit. You know why it is called graveyard orbit? The communication satellites that die out, what do? You push it out. So it is too expensive to bring them down. So you just push it out and they go into graveyard orbit and they may drift into space. And what happens if Starlink satellites, or some low orbit satellites, they outlive their life? You push them down. So they will burn under friction when they come in the air. So that is how, because right now it is technologically, even though it is possible, but it is not economically feasible to bring the satellite down and do some repairs. So this is the way we are heading. So in telecommunication, always there were two approaches competing with each other. One is satellite communication, another is landline cables. So cables, we have fiber. There we are having satellite communication. So at some point, one of them has the edge. Both of them have their own advantages and disadvantages. So we will have to see who wins. Actually, there is nobody is a winner, only leaders. Some point land communication dominates, some point wireless communication dominates. Now we will switch our focus to another application, that is automation and robotics. The word robot was not actually coined by a scientist. It was coined by a Czech author. In his play, it was a Czech play where he had imagined humanoid servants and he called them robots. And that is how the word robot came. Similarly, the word robotics was also coined by another science fiction, very famous science fiction writer, Isaac Asimov. This happened in 1942. Now let me pause and ask you a question. Industrial automation, when did it start? Can you take a guess? When would have been the first industrial automation happening? 100 years from now? That is, let us say, early 1900s? Or before that? How much before that? Yes, next. 1804. See, what you see is a loom. Loom is used for making cloth. So during those days, cloths were made using hand looms. And for making pattern on the cloth, different types of threads had to be woven. So making pattern was a very tedious job. And it was a highly skilled work. That is when this French entrepreneur, Jacquard, came with an idea that if you have a card, on the right side you see there are a stack of cards. Cards are having holes in it. If you use these punch cards, and as the loom advances, the actuators which can pass through those holes will be engaging the threads. So using this, they automated the process of weaving. Totally mechanical system, no electronics, no sensors. So this is the kind of first kind of automation seen in the history. Later, traditional robotics, as we call, the first robotic arm, it was developed in USA by George DeWall. It is called Unimate in 1959. This was used by General Motors in their car assembly plant for holding the vehicles during welding, moving material and all that. But this is a very rudimentary and a big, sluggish hydraulic robotic arm. The classical robotic arm that we see today came from Stanford. So this is the 6DOF robotic arm that we see today. It was designed by Victor Shaman in 1959. The concept holds good even today. So with this actually brought in electric motors and a clear 6 degree of freedom robotic arm. Now when we are talking about robotics, we cannot ignore the Japanese. So when the 6DOF robotic arm came, industrial robots picked up. And the most common application in industry is pick and place. You have to move objects between stations. You have to place objects for machining. So when it comes to pick and place robot, we generally don't go for a 6DOF robot. We go for another configuration, and that is SCARA. So we all know what is SCARA. It is selective compliant. We have compliance in a particular degree. Okay. So SCARA was a Japanese concept. It came from this university, Yamanashi University, and this concept has picked up so well that even today all pick and place robotics is happening because of SCARA robots. Even in some of our applications we have used SCARA robots. Now I will give you an example where we had to use robotics, and a typical 6 degree of freedom robot was used to do this job. Okay, in nuclear industry we use something called as heavy water in Indian nuclear power plants. Okay, what is heavy water? Heavy water is water where instead of hydrogen, the second isotope of hydrogen, deuterium, is used. Now when this heavy water is used in a nuclear plant, some of it undergoes transformation and becomes the third isotope, that is tritium. So tritiated heavy water is radioactive. Now periodically this heavy water has to be upgraded to maintain the isotopic purity. Now when this heavy water is transported in steel drums, and if you look at the top of the drum, you have lids on that. So these drums are actually brought to the upgradation plant, the lid is opened, and the heavy water inside that is taken out by a evacuation mechanism. Fresh heavy water is filled and the cap is put. This whole process exposes the operator to some amount of radioactivity, because the moment you open, water vapor will start coming out, which will be containing tritium in it. So the idea was to automate this process. Now how do we automate that? So we need a 6 DOF robot to come, uncap the drum, then put a arrangement, and after for evacuation, put an arrangement for filling, and then put the cap back. Now how do the robot know? How does the robot know that where the cap is located? So if you look at the robotic arm, and the end there is a laser scanner. So the robotic arm is also carrying a laser scanner. The laser scanner will scan the top of the drum, and yes, next, what we get is a point cloud of data. Now if you look at this point cloud of data, we can see the cap. So we have to use certain data processing algorithms to locate the ridge from the point cloud and to fit a plane. Once you fit a plane on that cap, then we will be able to get a perpendicular vector to that plane. Now why this is important? Because the top of the drum is not flat. It is slightly circular. And not only that, during use, the drum gets disfigured. The cap orientation might change. In order to open the cap, the robot has to hold the drum in an axial direction. So we have to find the orientation of the lid. So that is done using the data from the laser scanner. It comes to a back-end computer which does this calculation and finds the vector which is actually perpendicular to that. And then the robot orients itself, removes the cap, puts the mechanism for emptying, and then fills the drum and caps it back. I will show you a video where the robot is actually decapping the drum. Play. Back. Play कीजिए. So this, you can see the stainless steel drum. You can also see the cap. You can see the line of the laser scanner. The robot scans the cap. Okay, it finds where the cap is located. Then it finds the ridge. Uploads the point cloud to the computer. The computer calculates, finds the vector, tells the robot which is the perpendicular direction. The robot orients itself, brings the gripper, and then approaches the cap. So it will orient, approach the cap, grip, and then slowly unscrew the cap. While unscrewing the cap lifts. So the robot has to move backward. So the robot has to work in a compliant mode, take the thing, go, place it on a tray. Similarly for recapping, it has to pick from the tray, come to the calculated position, in the calculated orientation. This is the trickier part. Unscrewing is not the trickier part. The trickier part is because the thread has to match. Unless it comes in the proper orientation, the thread won't match. It screws it and fixes that. So this is where you find the flexibility of having a 6 DOF robot. Next. Now, when we talk about robotics, we cannot ignore manipulators. Manipulators are workhorse of any industry that is handling hazardous material. So for us in nuclear industry, manipulators are the workhorse. What are these master slave manipulators? There are actually two robotic arms. One which is there inside is called the slave. The one which is outside is called the master. Both of them are connected through a through tube. The operator stands outside in a well shielded environment. He uses the slave, and the master he uses the master, the slave just follows the master so that he can carry out any activity. Next please. Next. So this is how the arrangement looks like. There will be a shielding window, two arms for the master, two arms for the slave. The operator will hold both the arms and use the slave arms for handling radioactive substances. Next please. So this is how a typical radiation processing facility will look like. Series of windows, series of master slave manipulators. So the problem over here is the master and slave are mechanically coupled. So when they are mechanically coupled, the flexibility is lost. They have to be in one line. So why not decouple them? So the older design was to use a mechanical coupling, whereas the newer design, this is the older design where you have mechanical coupling, and next, newer design, we decouple them. Then how do we connect? There are motion sensors, potentiometers, encoders, resolvers on the master side, which will actually sense the master movement. And there is a control servo mechanism in between. Through the servo, the signal is given to the slave. There are motors on the slave which will actually move the slave arm. So now the master and slave have been decoupled. So this is the typical servo manipulator configuration. Next please. So here what happens, you can mount the slave anywhere, master can sit anywhere, you can use a CCTV camera to see what is happening and use the master to do the job. Why mount it? We can even, next, hang it on a crane, take it anywhere you want and still do the operation. But there is a tricky part in this. In a mechanical manipulator, because both of them were connected together, the operator actually gets the feel of the job. If he is lifting something heavy, he feels the weight. If he is pinching too much, he feels it. Whereas over here, the job is done by motors, so you just don't get the feel. But without this feel, you can make mistakes. So this is what is called force feedback. You need force feedback. That is the trickiest part in a servo manipulator. So what you have to do is, you have to sense the force being applied, either using a force sensor or by measuring the current of the motor. So once you get to know how much force is being applied, you send it back to the master and use the opposing motor to oppose the operator. And that is how this whole servo loop has to be balanced very critically to get a proper force reflection. So that is the technology behind the master slave manipulators. Next please. Okay, now we will come to evolution of computing. So what you see over here is the first electronic digital computer made in 1946. This is called ENIAC, Electronic Numeric Integrator and Calculator. This computer was built using vacuum tubes. It was built during the Second World War. The idea was to use it for calculating trajectory of shells, projectile motion. So this had very limited application. It had very limited capability, computing capability, but still it was a big achievement in those times. As soon as semiconductors started coming in, then the computers were built using semiconductors. In came IBM, the famous IBM 70 series. They started in the 60s. You can look at this computer, look at the background. What you see in the background are all tape. The data was stored in tapes during those days, huge tape drives. So this is how the early IBM mainframe machines, they looked like. Then came integrated circuits. When integrated circuits came, a new series of computers, next please, called the mini computers came into picture. And this company, DEC, Digital Electronic Corporation, was the leading manufacturer of mini computers in those days. and DEC PDP-8, PDP-10, PDP-11, PDP-12, these series of computers were considered to be the state of the art. This was somewhere in 1970s. After that, the microprocessors came, then came IBM PC, Macintosh, then our laptops and all modern equipment. And so, we come to the modern era of computing, where we have high performance computing, parallel processors. Now let me ask you a question. Which is the fastest computer today? Any idea? Any guesses? Which is the fastest computer today and how fast it is? How many floating point operations per second does it do? Okay, high performance computing, there is a list called top 500 list. The top 500 list keeps getting updated. So as of now, the winner of the top 500 list is, you can see this curve shows how the top 500 has been progressing. The y-axis is actually gigaflops. It is not just flops, it is gigaflops. So in 1995 we were close to 1 gigaflop. Then from 1 gigaflop we went to 10 gigaflop, 100. Then we came to teraflop. After teraflop, 10 teraflop, we came to petaflops. And then today we have crossed the petascale and we have entered the exascale, that is 10 raised to power 18. So by 2025, the fastest computers have crossed 1 exaflop. And who has done that? Next slide. This is the fastest machine today. This is called El Capitan, made by HP Enterprises. It is based on Cray technology. It uses AMD processors, more than 11 million cores. Its computing speed is 1700 petaflops or 1.7 exaflop. There are only 3 computers in the world which have crossed the petascale to exascale. The fastest one is El Capitan. It is installed in Lawrence Livermore Laboratories. The second is in Oak Ridge National Laboratory. That is also made by HPG. That also uses AMD processor. The third one is also in America. That is using Xeon, Intel Xeon processor. The second is at 1.3 exaflops. The third is at 1 exaflop. So in this top 500 list, now if you look for our Indian participation, we also started this high performance computing, especially when America denied Cray computers to us. We needed Cray computers for several applications. One of them was weather forecasting. Americans thought that we will be using that to do nuclear calculations. So they denied, and as a result, several agencies took up this job. CDAC's computer is the fastest today. So the CDAC computer is at 8 petaflops. It hasn't come to the hexaflop scale. It is at 136th rank in the top 500 list. Now, naturally the question comes, why don't we try to reach there? Shall we try to reach there into the exascale? So BARC also, we have a high HPC system which is at 1.5 petaflops. It is called Anupam. So Anupam Atulya, the latest model, is at 1.5 petaflops. So when I was discussing this with my colleague who is heading the computer division, I asked him that why not try to go for a much bigger system. Then he said, do you realize what all things goes into building this computer? Now let me ask you a question. Can you take a guess? What is the power this machine will be guzzling? How much power this machine will be? Our typical desktop computer uses how much? 300 watts? 400 watts? How much will this machine be using? Yes, please, louder. This uses 30 megawatt. This one machine is going to use 30 megawatt. So if somebody gifts this machine to your college, you will have to build a power plant to power it. 30 megawatt can power a small town. That is the kind of power this supercomputer uses. When it is doing 1.7 exaflop calculations, it will be guzzling 29.6, approximately 30 megawatt. So high. Yes. So, high performance computing doesn't come with just computing. You also need power behind it. Next, please. Next, please. Now let us come to the internet. I am not going to internet because you are all aware. Many of you will be knowing more about internet than what we know. But I just want to turn your attention to what goes behind internet. So when we see all the glossy interface, high speed performance, what is driving internet today? The first answer will be high speed network devices. You have high speed switches, 100 Gbps switches. Is it only high speed devices? The moment we type google.com and give a search command, in fraction of a second we get the result. There may be a million users doing the same thing. All of them are getting that result. How is that happening? That is happening because of the huge investment they have done and the large backend servers. Next, please. So behind every fast responding website, there are backend servers. When you say backend servers, huge computing systems, large amount of racks, lot of engineering going into building them, maintaining them. Next question is, are servers enough? Next, please. You also need data centers. Everything is on cloud today. Everybody wants cloud storage, whether it is Amazon Web Services or Apple Cloud or Google Drive. Everything is on cloud. The cloud comes not because of some isolated computers here and there. You need huge data stations. And again, these data stations have to be maintained. So, for all the IT which is going in the front, you have a lot of engineering going into the background. Now just let us go behind the rack and see how does it look like. Next, please. You will see maze of cables. This is only one rack. Every server station will be having tens and dozens or hundreds of racks. And when we talk about 100 gigabits or we talk about 1 gigabit Ethernet, the data has to flow through cables, whether it is through fiber or copper. A lot of engineering goes into making a Cat6, Cat6e cable. A lot of design has gone into it. Not just one rack. Next, please. There will be maze and maze of cables. So all these engineering efforts goes behind maintaining a server station or a data station. Now, when we were talking about the evolution of telecom, I narrated an incident where they tried to run a cable across the Atlantic. Today's internet is connecting the entire world because of several dozens or tens and tens of such submarine cables. Next, please. This is how the cable landscape looks today. Almost every water body has got cables running through them. All of them are submarine cables, buried under water, maintained so that we don't lose our internet. So next time when we look at internet, we should also imagine the infrastructure that is going behind that. Next, please. Next comes the power usage. How much power does the data center consume? This is the statistics from 2020. In 2020 alone, data centers used something like 200 to 250 terawatt hour of power, which is more than power consumed by many countries and as good as power consumed by developed countries like UK. So all this comes at a cost. There is a lot of engineering going behind this. And again, as I told in the case of Klystron, over here also, all the power is not getting translated into computing. Next, please. It also becomes heat that has to be cooled. These data centers or backup servers or the web servers, they need huge air conditioning and cooling plants behind them. Now, do you know how much power goes in all this? Next, please. This is a pie chart. which shows how the power consumed by data centers and these IT resources go. 37% goes for the IT load, 3% for lighting. What about the remaining 60? 10% is lost because of conversion, AC to DC, DC to DC. And almost 50% goes in cooling and taking away the heat. So if our country wants to set up a huge data center, rivaling that of, OpenAI or Google or Apple or Amazon, we need power for that. So unless we have power stations pumping power into the grid, or at least captive power plants which can maintain this, it is just not possible just by IT infrastructure to set up this level of systems. Next please. So okay, let me sum up. We have gone through different technologies, seen its role. We have seen how the society evolved from a hunter-gatherer to agrarian to industrialized to knowledge-based society. Now I want to ask you something. What will be driving the knowledge-based society tomorrow? Next please. Will it be software and artificial intelligence? Next. Will it be robotics? Next. Will it be electronic systems and computer hardware? Or will it be telecommunication? Or will it be power engineering? Or will it be thermal design and engineering? I am putting this in your favorite format as a multiple choice question. And whenever we are faced with this multiple choice question, we always look for one favorite answer of ours. Next please. Will it be all of the above? So I think I have put some points for you to ponder, to understand whenever we see any technology, how a particular technology is evolved with the help of other technologies in the support. And I hope this will lead you to think, analyze, and then take a decision whenever choosing a technology or choosing a career path. Thank you very much. Next.
Thank you very much, sir, for enlightening us with your knowledge and perspectives. Your talk has offered valuable takeaways and truly emphasized the importance of continued innovation. To express our gratitude, may I now invite our department HODs, Kavita Tiwari ma'am and Sangeeta Prasanna ma'am, to present mementos to our esteemed speakers. As we draw this session to a close, I take this opportunity to deliver the vote of thanks. We are immensely grateful to our speakers, Sri A.K. Balasubramanian and Dr. Padmanabhan Mahadevan, for sharing their wealth of knowledge with us today. A special thanks to INAE for facilitating this wonderful session. To our principal, faculty, organizing team and logistics team, and our students, thank you for making this session meaningful through your presence and participation. We look forward to many more such sessions in the future. Thank you and have a great day ahead. Does the audience have any questions for the speakers?
Sir, I have a question. how this INAE is going to be useful for our engineering students at this moment when they are in third year, on second year or final year, and when they are graduating soon. How this can be collaborated with our college, number one. Number two, second question is that what skill sets that students should start developing, because sir has very nicely explored about the technology right from the beginning. I really appreciate. After a long time, I have interacted with such a nice session, which focused really very nicely for the fundamental concepts of technologies. So, what skill sets that students should start developing right from their undergraduate level?
Okay, as I said earlier, Indian National Academy of Engineering promotes engineering activities. So for students, there are certain competitions arranged, and as they grow further into their career, there are possibilities of INAE Young Fellows, Young Fellowships, which are, they are young fellows are selected based on certain procedure, certain required qualification and professional work. So they can get into this professional body at a little later stage. And as I showed earlier, there are some scholarships and student promotional activities, the details of which I can share you later in a proper format. Okay, so that's about getting into the activities of INAE. Now, with respect to your second question, I think I will pass it on to him.
Now, as far as developing skill set is concerned, see, again, first of all, we have to decide what is it you want. Okay, because skill set is different for different domains. Now, all of us come with our own, what you should say, knack or our own aptitude. For somebody who wants to make a career in, let us say, areas which requires a lot of public participation, communication skills are a must. Okay, we just cannot ignore that. We may be good at something, unless we are able to speak it out, put it in a way that the other person understands, we will not be able to do a good job at it. So most of the industries where we have to work, there are very few roles where you will be totally in the back end. When you are in the back end, then your communication skills aren't that important. It's the technical skills that comes into play over there. Now again, even before that, when you are going to face an interview, you should be able to express yourself properly. So communication skills are a must. Then coming to your technical skills, there again you'll have to look for where you are going. Suppose you are going to an industry where I'm talking industry in general, where you will be mostly working on O&M, that is operation and maintenance of an industrial facility. There your broad knowledge of technical skills is what is important. But if you're coming to a R&D industry, then fundamentals are very important. So like if you are planning to apply to BARC, RDAE and all that, what we suggest is keep your fundamentals strong. Okay, the basic concepts have to be very strong. So that is the kind of skill sets when you look for when you're going to any research institution. It need not be just BARC. Even if you are applying for a high-end research institution abroad, there also what they look for is your analytical skills and fundamentals. These things have to be very powerful. Now, for if you are going to other type, the operating plants or industries where it is O&M or these kind of activities, your overall technical knowledge as well as your communication skills are very important. Now, when if you are going to an electronic industry, then there are things which electronic industry today looks for. For example, competence in VLSI design, VHDL, that is very much looked after. Then if you are planning to come to electronics industry, going towards RF, a good knowledge of electromagnetics, that will help a lot. If you are going to be there in a process industry for people who are from instrumentation background, then your from basic understanding, your aptitude to understand the process is very important, as well as your instrumentation knowledge. So your ability to learn. See, when you go to a plant, it may not be what you have learned over here. So you should be able to grasp the process very well. You should be able to collaborate with others. So when you go to these kind of plants and industries, you go there as an instrumentation engineer, you will be dealing with a chemist, a chemical engineer, a mechanical engineer, electrical engineers, and so on. So you should be able to understand their lingo, their terminology, and converse. So I'm just telling you, when you are talking among yourself, people from one branch understand each other very well. But when you talk across the branch, their terminology changes, your terminology changes, and having a technical dialogue doesn't go that well. But if you look at professionals, people coming from the plant, they will very easily switch from pound for square inch to kilovolts to milliamperes and to pH values. So this kind of interoperability is something which will take you a long way. So actually you don't have to sit to develop this, just have an open mind. Talk among each other, talk to all your faculty members, make use of opportunity where you get to talk to people who are in the field, and this will help you a lot. Okay, so that is for instrumentation, electronics people, and computer science. We all know what is needed as on today. What my suggestion would be, don't aim for low-end developing work or maintenance works. See, the maintenance and low-end development work is the one which will be eaten up by automation fast. You have to look for niche segments. So this happened to every industry. See, at one point of time, in manufacturing industry, the manufacturing skill of an operator was important. The moment numerically controlled machines, CNC machines came in, that whole thing vanished. A computer was able to do that. So today, that automation is actually entering into your low-end development work also. So apart from this, as I stressed, communication skills are very important. Your willingness to learn, willingness to discuss with others, and pick up. So all these things will make you a well-rounded engineer to make you successful in your career. Thank you.
Sir, my question was about that cryogenic computation which you mentioned. You mentioned that we need an entire power plant to work that computers and all. So my question is, can't we use neuromorphic computing over there? Because I have done a project in my internship where we have simulated a simple Euclidean distance for which a ThinkPad like computer need 50 watt, whereas neuromorphic computers only need 1 watt.
Yes, see, those are all the kind of things which are, right now in infancy, and it is going on. So it is quite possible that in near future, or if not near future and little more into future, we will have to come into those kind of effort. Today, as I said, we have a top 500 list for supercomputers. There is also a top green 500 list. Okay, that actually kind of normalizes your computing power with the power consumed. So this kind of activities are going on. So trying to find out a computing device which will use a computing paradigm which will use lower power. But as on today, when we say as on today, general purpose computers are the CPU and GPU based systems which are there today. And today's problems, only they are solving. And my point was that many a times we don't need this kind of computing power. So when in BRC also, when we tried to ask for money, so all these things need money. So we made a proposal saying that we will go for a 15 petaflop machine. How much money you need? 500 crores. There is that kind of money which goes into this. then the immediate question is, what will you do with this computer? Do we have problems that need this kind of computing power? See, a problem can be solved by a 500 petaflop machine in, let us say, 1 full day of computing. The same thing will be solved in 4 to 5 hours of computing in a hexaflop machine. So do we need to save time at this cost and this money? So these are all cost benefit analysis that goes into this. Many of these computers are there to show that we can do it. Some of them are having real applications. But see, even this machine will not be running at 1.7 exaflops all day long. Occasionally, for a small time, it may have to go to that power. Otherwise, it will be doing at a lower this thing only. So if you see olden days, people built huge monuments. Okay, we remember them for those monuments. So these are also monuments of the modern day. And this race is going on. I'm sure in another 3 to 4 months, somebody else will take over El Capitan. So because El Capitan took over only 2 months ago, 3 months ago. Yes. So this actually brought HP into, see, Japanese computers were leading a couple of years ago. Chinese computers were dominating the top 500 list till USA posed sanctions on GPU exports to China. After that, that domination reduced a bit. So now top 3, all the 3 are American computers. They are HP. And one more just thing or what I want to tell is, technology which gets adapted in the world is not always the best technology. So when we have multiple competing technologies, which one will be adapted in the world? Time and again we have seen that there are geopolitical factors and economic factors which comes into this. One prime example was, we used to have a videotape. Okay, during our days, video used to be recorded on tape, which was called VHS. The VHS format was not the best format at that point of time. Betamax was the best format. But VHS was having a big lobby behind them. So VHS got adapted. Same happened with DVD. Okay, so this is how it is. See, IBM came up with IBM PC. PC was an open architecture. Everybody started copying and building PCs. Then IBM found that they are not making money out of it. So they came up with another system which was superior to this. That was called PS. It had operating system called OS1 and OS2. That was much superior to it, but nobody has heard about it. Nobody bought that. So which technology will come up depends on so many factors. So these high performance computing is more like muscle power to show that, okay, we can do this. So that's how it is. Green technologies again need backing. Like you found out the neuromorphing computing. There are so many such initiatives are there. Let us see. Let us hope things come up. Okay, thank you.
The session is done. Everybody can disperse from the back door, please.